I'm going to take this time to go through and give you some commentary along with the exam review. And let's start with this. At this point in time, every time I sat down an exam for anything, I would sketch out these pictures. And I would go all the way up to the 45. That's 0.707. And I would make the tangent of 1. I would go to the next one below it, 0.866 and 0.5. And I would know that that is 1 over the square root of 3. And I would go to here at the third one, 0.9659 and 0.2588. And I would know that I don't know what that value is, but I would know that this is pi over 12, and this is pi over 6, and this is pi over 4. And I would remind myself about the flippy nature of all this. Flip and flip and flip and flip and flip. I would start with that. I would next go to the very least to the circle of units, not only in terms of specific gravity, force, or CE, and unit weight. So knowing that unit weight would be pounds per cubic foot or newtons per cubic meter, but I would go to angular displacement and to distance and to area and to volume and to mass. Getting to force, I would go to work, I would go to power, I would go to pressure and torque and mass density with the knowledge of time. And then say to myself, unit lists, meters, square meters, cubic meters, kilograms, newtons, joules, watts, pascals, newton meters, kilograms per cubic meter, and newtons per cubic meter. And I would then go back and write unit lists. I would probably start switching in hours or degrees for some of these, but unit lists, feet, square feet, cubic feet, slugs, pounds pounds per second, pounds per square foot, pound feet, slugs per cubic foot, and pounds per cubic foot. Knowing, of course, that water has a unit weight of 62.4 pounds per cubic foot. I would start doing that before I looked at anything at all on an exam. I would also lay out some concepts of what y equals mx plus b, and remind myself that the negative reciprocal is minus 1 over m. I'd do a number of those things before I did anything. If I was had done survey, I would write down these values that I know that if I want to go from x, y, z, or specifically change in x, change in y, and change in z, I would know that I would like to know that the radial projected vector is equal to, the magnitude of that is equal to x squared plus y squared, square root, but the magnitude of the vector is equal to the square root of x squared plus y squared plus z squared. And then I would know that if I want to talk about this in terms of magnitude, azimuthal angle, and elevation angle as I cared, I would want to know that in fact elevation angle equals z over r prime, and theta, right? I'm sorry, the tangent of the elevation angle equals z over r prime, and theta equals y over x. And from that I might get to the point of knowing that z equals r, the magnitude of the vector, times the sine of the elevation angle, and r prime equals r times the cosine of the elevation angle, and x equals r prime times the cosine of theta, and y equals r prime times the sine of theta. I would sketch these things out and I would know them before I looked at anything that went beyond, and there's going to be a number of other things. But that said, let's go down and see if we can continue. File, new, no. So we had what we had for review. You were to know the circle of units, and you were to know the concept of vectors, specifically change in x, change in y, change in z, and how it can also be written in polar, r, theta, and phi, with one being a polar angle or an elevation or a zenith angle or an elevation angle, and the other one being an angle in the plane of definition, or the azimuthal angle. You would also want to know that if I have a vector of 5, 5, and 5, it can be also written as something that is a certain magnitude. So the magnitude of 5, 5, 5 is the square root of 5 squared plus 5 squared plus 5 squared. And the unit vector is in fact 5 over that same value, the square root of 5 squared plus 5 squared plus 5 squared, comma, and the x. That in the y, the square root of 5 squared plus 5 squared plus 5 squared. And once again, 5 over the square root of 5 squared plus 5 squared plus 5 squared. Or any vector can be written as its magnitude. So any vector v can be written as the magnitude of the vector times the unit vector, with the unit vector being the vector. The unit vector is equal to the vector divided by the magnitude of the vector. And so you'll see that becomes incredibly important as you try to solve some of these problems and mix back the algebra with the graphics, where in fact understanding a vector as a magnitude and a direction defined by a unit vector makes things much more straightforward in a calculator. Finally, on the things I might write down would be, at very least, this knowledge of progression. Don't want to do that. Close that up. Of a circle. Its angle, its perimeter, its area, essentially its volume, and its second moment of the area, having a progression for the unit circle, having values of 2 times pi times the, for instance, for feet to the 0 power, the perimeter being 2 pi times feet to the first power, the area being pi feet squared, the volume being 2/3 of the enclosing cylinder, or what turns out to be 4/3 pi feet to the third, and the second moment of the area being pi over 4 feet to the fourth, all of course coming from that formula where this S equals r theta, giving you the internal angle of a circle being 2 pi, the perimeter being 2 pi r, coming from the definition of pi, the area being pi r squared, the volume being 4/3 pi r cubed, and the isomota being pi over 4 r to the fourth, and wanting to add that the area of surface of a sphere being equal to 4 pi r squared. So knowing one of these doesn't get you far, knowing all of you gets you pretty far. I would start and write all those down. Therefore, if someone asked me a question about one or the other, I could go to any one of these equations and have a forced choice, particularly looking at the units. If someone was asking me something about area, I would grab area. I wouldn't give something that gave me a circumference. Pretty common error, but almost not understandable at this point to mix up area and circumference on a regular basis. That said, considering how powerful arrays are, once again going File, New, no, how powerful arrays are, realizing that we have learned the difference between a transformation matrix and another matrix are this. The transformations always start with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. In the world where in fact we stack our points, our point matrices as x sub 1, y sub 1, z sub 1 with a 1 chaser, x sub 2, y sub 2, z sub 2 with a 1 chaser, x sub 3, y sub 3, z sub 3 with a y chaser, and x sub 4, y sub 4, z sub 4 with a 1 chaser. And remembering smartly, I might always add a fifth point and never do a 4 by 4, so we would have two visual. And of course, knowing this can be as large as you want it to be. All right. Realizing by doing this, many times you're just transforming 1 point or 2 points, a line, or 3 points, a triangle. If you're going to transform a rectangle, add that fifth point someplace in the middle, perhaps the centroid, so that your mind does not get confused. But also then remembering that in most programs or many programs, you're going to stack these up by address 0, 1, 2 to 15, with this being space 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, or to count backwards, minus 1, minus 2, minus 3, minus 4, where in fact this can also be written up as position minus 1, minus 2, minus 3. In that case, you do get a minus 16 position. If one does that, then that next discussion of what happens in transformation matrices does not get very difficult, and that is this. In the matrix, you have nested inside the matrix what's often seen as the rotation scale matrix. That's the rotation scale matrix. Inside of it you have the translation matrix, for instance here, moving at 1 in the x, 0 in the y, 0 in the z, and then along the bottom, as we know, these kind of placeholders. And then you can know that if only you would then compare whatever matrix is thrown at you by highlighting how many things are different from the identity matrix. So let me now go forward, File, New, No. If in fact you have an identity matrix sketched someplace on the page in your brain, and that's why in fact the repetition of doing it this way does help, then you can compare. So if just this number is changed, you know it's a scale in the x. If just this number is changed, you know it's a scale in the y. If just this number is changed, you know it's a scale in the z. If just this number is changed, you know it's an overall scale. If just this number is changed, you know it's changed its position in the x, changed its position in the y, changed its position in the z, and any collection 3 thereof or 2 thereof. If in fact these are all changed, you know that you have locked up the z and done either a rotation or a flip. If these are the ones that are changed, you know you have locked up the x and done a rotation or a flip. And if in fact these remain intact, you know whether you've done a rotation or a flip. And then knowing the two standard values and going back to your knowledge of the unit circle and even going all the way up, you can then decide whether the pattern that you see that is changed is what you know for rotation, being cosine minus sine, sine, cosine, if in fact it is a rotation, or cosine of 2 theta, sine of 2 theta, sine of 2 theta, minus cosine of 2 theta. So you then can evaluate these things that are changed and come up with some perception or knowledge of what's going on. But in fact, why wouldn't you then have a shape in your calculator that you can understand and then just run the matrix so you have a redundant system? So asking your calculator a question that it knows the answer to sometimes means pre-programming. Not just your brain, but also your tools. So that said, you might do the same thing for both the world where your transformations are done by a 16-place matrix, 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, where some things, and sometimes it's more than one thing changes, some things might change, that might be 8 and 10 and 100, or in fact, this would be a translation, or in fact, if your transformation is going to be some scale where you've mapped everything in a set of complex coordinates, and then with this being the scale and this being in fact the rotational angle. Once again, pre-program your calculator so you can, or your computer or your brain, so you can presuppose and then test. Finally, and this I think was probably the most striking for me, if in fact you know something is 50 pounds per foot, how do you go about figuring out what that cross-sectional area is? I would assume one of the most easiest ways to do it might be to assume that you had something that was 12 inches by 12 inches by 12 inches. So if something was 12 by 12 by 12 inches, you know it weighs 490 pounds. And so if you go ahead and realize that you have something that's 50 pounds, right, but it's still 12 inches deep, you can then do a ratio. So this division of 12 by 12, you can take that 490 divided by 12 and know that something that is 144 square inches is going to be equal to something like 490 divided by 12 is going to be 40 inches, 40 plus, about 40 plus square inches. So if something is 40 plus pounds. So if something is 50, we're going to have to edit that out because that is not correct.